Mars doesn't care about our dreams. They're selling you Mars like it's humanity's salvation. They're not telling you about the bone loss, the radiation sickness, or the psychological collapse. Mars isn't just another frontier. It's a battle for survival against one of the most hostile environments humanity has ever faced. And here is a question. What is the single most precious thing you would want to bring to Mars? Comment down below. I'll pin the most creative answer. Now let's begin. So here's what most people don't understand about Mars. When we see those stunning images from Perseverance or Curiosity, when we hear about ice deposits and ancient riverbeds, we imagine a place that's almost livable, but we couldn't be more wrong. Mars is approximately half the size of Earth, with gravity that's only 38% of what you experience right now. Its atmosphere? So thin it might as well not exist. Just 0.6% of Earth's atmospheric pressure. That means if you stepped outside without a spacesuit, your blood would literally boil. Not from heat, but from the lack of pressure. Your body would swell. You'd lose consciousness in about 15 seconds. Death would follow in roughly 90 seconds. But let's say you're suited up. You've got your state-of-the-art Mars habitat, your life support systems humming along perfectly. You think you're safe? Think again, because Mars has spent the last 4 billion years perfecting ways to destroy anything that dares to live on its surface. Let me take you back to a discovery that changed everything we thought we knew about Martian colonization. In 2008, NASA's Phoenix lander detected something in the Martian soil that made scientists' blood run cold. Perchlorates, these chemical compounds made of chlorine and oxygen, are scattered throughout Martian dirt at concentrations of about 0.5%. That might not sound like much, but here's the problem. Perchlorates are toxic to humans. On Earth, we use perchlorates in rocket fuel, fireworks, and explosives. They're so reactive that they can damage your thyroid gland, disrupt hormone production, and potentially cause developmental problems. The European Space Agency has safety limits for perchlorate exposure set at 0.7 milligrams per kilogram of body weight per day. A recent comprehensive study published in GeoHealth in 2025 found that just inhaling a few milligrams of Martian dust would exceed the recommended safe dose we follow here on Earth. Now imagine you're growing food in Martian soil. Those perchlorates get absorbed by your plants. You eat the plants, day after day, month after month, year after year. What happens to your thyroid, your metabolism? Your ability to think clearly when every decision could mean life or death. And perchlorates are just the beginning of Mars's chemical arsenal. The dust itself, that fine, rust-colored powder that covers everything, is approximately 3 micrometers in diameter. To give you perspective, that's about 4% the width of a single human hair. This isn't beach sand. This isn't desert dust. This is particles so microscopically small they can penetrate deep into your lungs, slip past your body's defenses, and enter your bloodstream. Apollo astronauts who visited the moon reported immediate reactions to lunar dust, watering eyes, scratchy throats, symptoms resembling hay fever. Harrison Schmitt, the geologist on Apollo 17, experienced such severe reactions that NASA conducted extensive studies afterward. But here's what keeps Mars scientists awake at night. Martian dust is potentially far more dangerous than lunar dust. And we're talking about exposure not for 3 days, but for years. A groundbreaking study led by Justin Wang and an interdisciplinary team from the University of Southern California, University of Colorado Boulder, and NASA's Johnson Space Center examined exactly what Martian dust does to human tissue. Published in February 2025, their research revealed what they called a laundry list of dangerous compounds. Silica, the same substance that gives coal miners silicosis, a progressive lung disease that scars your lungs and makes every breath a struggle. On Mars, silica makes up a significant portion of the dust composition, iron oxides, the compounds that give Mars its red color. These aren't just pigments. They make Martian dust magnetic and electrostatic, meaning it clings to everything: your suit, your equipment, your habitat walls. You can't simply brush it off. It sticks. It accumulates. It finds its way inside no matter how careful you are. Gypsum, calcium sulfate that can cause respiratory irritation with prolonged exposure. And then there are trace metals: arsenic, chromium, beryllium. While concentrations might be relatively low, we're talking about chronic exposure over years. Nobody has studied what that does to a human body because nobody has ever experienced it. But the dust's chemical composition is only half the story. The other half is even more insidious. Mars has no global magnetic field. Earth's magnetic field acts like an invisible shield, deflecting most of the dangerous radiation that constantly streams from the Sun and from distant cosmic sources. Mars lost its global magnetic field approximately 4 billion years ago, a story we'll come back to, because understanding why Mars died is crucial to understanding why living there is so dangerous. Without that protective shield, radiation bombards the Martian surface every single second of every single day. We're talking about two types of radiation here. First, there's solar radiation, high-energy particles that the Sun hurls into space during solar flares and coronal mass ejections. Second, there's galactic cosmic radiation, particles accelerated to nearly the speed of light by supernova explosions and other violent cosmic events, traveling across the galaxy until they slam into Mars. NASA's Curiosity rover has been measuring radiation levels on Mars since 2012. The findings: an astronaut on the Martian surface would receive about 0.67 millisieverts of radiation per day. That might sound abstract, so let me translate it into something more concrete. In a single Martian year, which lasts 687 Earth days, you'd absorb approximately 230 millisieverts of radiation. The annual radiation dose limit for nuclear power plant workers on Earth is 50 millisieverts. For the general public, it's 1 millisievert per year. Do the math. Living on Mars means absorbing more than 200 times the radiation exposure considered safe for ordinary people on Earth every single year. What does that radiation do to you? It tears through your cells, damaging DNA, increasing your risk of cancer exponentially. It affects your central nervous system, potentially causing cognitive problems. It damages your cardiovascular system. And here's the cruel irony: that same radiation exposure makes you more susceptible to pulmonary fibrosis, a condition where your lung tissue scars and stiffens, making breathing progressively harder. And what exacerbates pulmonary fibrosis? That's right, inhaling fine dust particles. Mars creates a perfect storm of hazards that amplify each other. You might be thinking, okay, we'll just build better habitats, thicker walls, better filtration systems. We'll shield ourselves from the radiation and keep the dust out. Absolutely, we need to do that. But here's what the engineering calculations reveal, and this is where the terrifying reality really crystallizes. To effectively shield against galactic cosmic radiation, you need mass, lots of mass. Water works well. About 5 meters of water can reduce radiation exposure significantly. Rock and regolith work too. You'd need about 3 to 4 meters of Martian soil piled on top of your habitat. Let's say you're building a habitat for 6 people, a typical Mars mission crew size. You need living space, working space, storage, life support systems. A modest facility might have a footprint of about 200 square meters. To shield that with 3 meters of Martian regolith, you'd need to excavate, transport, and pile approximately 1,800 metric tons of soil on top of your structure. Do you know how much mass NASA's Perseverance rover weighs? 1,025 kilograms. We celebrated sending 1 ton of equipment to Mars. Now we're talking about moving nearly 2,000 tons of soil for a single habitat. using equipment that also needs to be transported from Earth, and that's just to protect against radiation. You still need to solve the dust problem, the perchlorate problem, the toxic chemical problem. You need airlocks that prevent even microscopic particles from entering. You need filtration systems that can catch 3 micrometer particles and need essentially zero maintenance, because maintenance requires going outside, which means more dust exposure, which means more health risk. Every system needs redundancy because there's no hardware store on Mars. There's no emergency supply ship that can reach you in days or even weeks. If something breaks, you fix it with what you have or you die. It's that simple. Now let's talk about something that sounds mundane but could kill you just as easily as radiation. Temperature. The average temperature on Mars hovers around -63 degrees Celsius. But averages lie. At the equator during summer, daytime temperatures can climb to a relatively balmy 20 degrees Celsius, t-shirt weather, right? Except the moment the sun sets, temperatures plummet to -73 degrees Celsius or lower. You're looking at temperature swings of nearly 90 degrees in a single day. Your habitat needs to handle these extreme fluctuations. Metal contracts in the cold and expands in warmth. Seals crack, joints weaken, every Martian day or sol, as we call them, each lasting 24 hours and 39 minutes. Your entire base experiences stresses that would tear apart most Earth buildings within weeks. And speaking of the cold, let's discuss what it does to you psychologically. Humans evolved under a yellow sun on a world where, for most of Earth's habitable zones, you can step outside and feel warmth on your skin, breathe freely, hear wind rustling through trees or waves crashing on shores. On Mars, you're imprisoned. You can never step outside without a suit. You can never feel Martian wind on your face. And believe me, you wouldn't want to, because Martian wind isn't refreshing. It's a reminder that the planet is trying to freeze you solid. The psychological studies conducted on Antarctic research stations, our closest Earth analogue to Mars isolation, reveal concerning patterns. During long Antarctic winters, researchers experience something called the winter over syndrome, depression, cognitive impairment, sleep disturbances, interpersonal conflicts. And those researchers know they can leave. They know rescue is possible. They can call home with only a slight delay. On Mars, communication with Earth has a time delay ranging from 3 to 22 minutes one way, depending on orbital positions. You can't have a conversation. You can't call home when you're feeling desperate and hear a loved one's voice respond immediately. You send a message and wait, and hope that when the response comes, it contains the comfort or information you desperately need. NASA and other space agencies have run isolation experiments. Shiza's in Hawaii, the Mars 500 simulation in Russia. These experiments consistently show that even carefully selected, highly trained individuals experience significant psychological strain after just months of isolation. We're talking about Mars missions lasting years, possibly decades if we're establishing permanent settlements. The psychological toll compounds every other danger. A depressed astronaut makes mistakes. A sleep-deprived crew member misses critical warning signs. Interpersonal conflicts lead to communication breakdowns, and on Mars, communication breakdowns can mean mission failure. Mission failure means death. But let's zoom out from the immediate dangers of dust and radiation and cold. Let's talk about why Mars is the way it is, because understanding Mars's past reveals something profound about planetary habitability and our place in the cosmic story. Approximately 4 billion years ago, Mars was radically different. NASA's MAVEN mission, the Mars Atmosphere and Volatile Evolution spacecraft, has been studying Mars's upper atmosphere since 2014, and the data paints a fascinating picture. Mars once had a thicker atmosphere, perhaps dense enough to support liquid water on its surface. Orbital imagery reveals dried river valleys, ancient lake beds, and possible ocean basins. Mars, incredibly, might have been a blue planet. So what happened? Why did Mars die? The answer involves one of the most fundamental requirements for keeping a planet habitable: a global magnetic field. Earth generates its magnetic field through the churning of molten iron in its outer core, a geodynamo that's been running for billions of years. This magnetic field extends far into space, creating the magnetosphere that shields us from the solar wind. Mars had a magnetic field once. We know this because certain regions of Mars's crust, particularly in the southern highlands, show remnant magnetization, frozen evidence of ancient magnetic fields. But roughly 4 billion years ago, Mars's core cooled. The geodynamo shut down. The global magnetic field collapsed. Without that shield, the solar wind, that relentless stream of charged particles flowing from the sun, began stripping away Mars's atmosphere, literally peeling it off layer by layer, molecule by molecule, and carrying it away into space. NASA launched the ESCAPADE mission, Escape and Plasma Acceleration and Dynamics Explorers, in November 2025, specifically to watch this process in action. The twin spacecraft activated their scientific instruments in February 2026 and are now measuring exactly how the solar wind continues to erode what little atmosphere Mars has left. Think about the timescale here. This process has been happening for 4 billion years and it's still ongoing. Every second, Mars loses approximately 100 grams of atmosphere to space. That might sound trivial. 100 grams is less than a candy bar, but multiply that by the number of seconds in 4 billion years. Mars has lost an atmosphere that might have been as thick as Earth's, leaving behind that pathetic 0.6% we see today. This is a dead planet, and we're talking about trying to live on it. Some visionaries proposed terraforming, engineering Mars back to habitability, making it warm, giving it a breathable atmosphere, perhaps even recreating oceans. It sounds like science fiction, but scientists take it seriously enough to run the calculations. And those calculations are sobering. A recent study published in March 2026 by Slava Turishev at NASA's Jet Propulsion Laboratory examined the feasibility constraints of terraforming Mars. The paper lays out the brutal mathematical reality. To create an atmosphere with pressure similar to Earth's, you need mass. Specifically, you need somewhere between 10 to the 17th and 10 to the 18th kilograms of atmospheric gases. Let me put that in perspective. That's 100 million billion to 1 billion billion kilograms. Where do you get that mass? Option 1. Release carbon dioxide frozen in Mars's polar ice caps and absorbed in its soil. Studies suggest you might be able to release enough carbon dioxide to create an atmosphere with a pressure of about 20 millibars, roughly 3% of Earth's sea level pressure. That gives you maybe 10 degrees Celsius of warming through greenhouse effects. It's not nothing, but it's nowhere near enough to let you walk around without a pressure suit. Option 2. Manufacture super greenhouse gases, compounds far more effective at trapping heat than carbon dioxide. Recent papers by Ansari and colleagues in 2024 and Richardson in 2025 proposed injecting engineered aerosols into Mars's atmosphere. Their calculations suggest these aerosols could warm Mars by 35 degrees Celsius, potentially bringing some regions above the melting point of water. Sounds promising, right? But here's what happened when other scientists ran those scenarios through detailed climate models. A paper published in March 2026 using the Mars WRF three-dimensional global climate model found that warming Mars triggers massive changes to its water cycle. For every 20 degrees Celsius of warming, atmospheric water vapor content increases tenfold due to sublimation from the North Polar Cap. This amplifies cloud formation, which causes nighttime warming in some regions but daytime cooling of up to 40 degrees Celsius in winter mid-latitudes. Water gets transferred from the North Polar region to the South Polar region, and these changes persist for decades even after you stop releasing warming aerosols. In other words, warming Mars doesn't give you Earth. It gives you a chaotic, unpredictable climate system that might be even harder to survive in than the frozen desert we have now, and we haven't even addressed the energy requirements. Turishev's study calculated that creating a breathable oxygen-nitrogen atmosphere, forget about just warming the planet, we're talking about air you can actually breathe, would require a minimum oxygenation work of approximately 10 to the 25th joules. To put that in context, that's roughly equal to all the energy humanity currently produces in 10,000 years. You'd need sustained power output in the hundreds of terawatts to petawatts range, maintained for centuries to millennia. We're not talking about building cities on Mars. We're talking about an engineering project that would consume the total industrial capacity of Earth for thousands of years. So terraforming isn't happening anytime soon, which brings us back to the original scenario, trying to survive in habitats on a hostile world. Let me paint you a picture of what daily life might actually look like for the first Mars colonists. You wake up in your sleeping pod, a space barely larger than a closet, because every cubic meter of pressurized volume costs money and mass to transport from Earth. The lighting cycles are programmed to mimic Earth's day-night rhythm because otherwise you'd experience circadian disruption that would wreck your sleep, your health, your cognitive function. You check the radiation monitor first thing. It's been a quiet night, no major solar events. Good. Last month, a coronal mass ejection sent a wave of high-energy particles toward Mars, and everyone had to retreat to the storm shelter, a smaller pod surrounded by water tanks that provide additional shielding. You spent 14 hours in there, cramped together with your crew, waiting for the radiation levels to drop to merely dangerous instead of immediately lethal. Breakfast is a protein bar made from algae and cultured proteins grown in the habitat's biological lab. It tastes like cardboard, but it provides the nutrients you need. Fresh food, real vegetables grown in Martian regolith that's been painstakingly cleaned of perchlorates, is a luxury reserved for special occasions. The cleaning process requires washing the soil repeatedly, which consumes precious water. Every drop of water is recycled, filtered, purified. You're drinking yesterday's sweat and urine. You try not to think about it. After breakfast, you suit up for an EVA, extravehicular activity. Today's task is routine maintenance on the solar panel array. Martian dust has been accumulating on the panels, reducing their efficiency by 15% over the past month. This dust is electrostatically charged, remember? It doesn't just blow away. You need to physically wipe each panel clean. Suiting up takes 30 minutes. Every seal must be checked twice. You go through the buddy system. Your partner examines your suit. You examine theirs. A single seal failure means death. The airlock cycles, and you step out onto the Martian surface. The landscape stretches before you in monochromatic rust tones. The sky above is that eerie butterscotch color, a result of suspended dust particles scattering light differently than Earth's blue skies. Earth's sky is blue because nitrogen and oxygen molecules scatter shorter wavelengths. Mars's sky is orange because those dust particles scatter longer wavelengths. It's beautiful in an alien, unsettling way. You walk carefully in the reduced gravity. 38% of Earth's gravity sounds fun, like you could bound around like the Apollo astronauts on the moon. But this isn't playtime. Falling damages your suit. Damaged suits mean compromised seals. Compromised seals mean death. Every movement is calculated, deliberate. You reach the solar array and begin cleaning. The work is tedious, exhausting. Your suit is bulky, your gloves thick. Fine motor control is nearly impossible. What would take 20 minutes on Earth takes 2 hours here, and every minute outside is another minute of radiation exposure, another opportunity for micrometeorite impacts, another chance for equipment failure. While you work, you keep one eye on the horizon. Dust storms on Mars aren't like dust storms on Earth. They can grow from regional disturbances to planet-encompassing monsters in a matter of weeks. In 2018, a global dust storm covered Mars for months, blocking so much sunlight that NASA's Opportunity rover, which relied on solar power, went silent and never woke up. That rover had been operating for almost 15 years. The dust killed it in weeks. If a global dust storm hits while you're living on Mars, your solar panels become useless. You're entirely dependent on backup power, nuclear reactors, battery reserves, and you're stuck inside your habitat, unable to go outside for maintenance, unable to fix anything that breaks, waiting for the storm to clear. Weeks turn into months, supplies dwindle, air recycling systems strain under continuous operation. The psychological pressure of confinement becomes crushing. But let's say the dust storm doesn't come. You finish cleaning the panels and return to the airlock. Here's where another terrifying reality emerges. You can't just walk back inside. The airlock protocol is rigorous. You spend 15 minutes in the outer chamber using brushes and compressed air to remove as much dust as possible from your suit. But remember, this dust is electrostatic. It clings. Some of it, inevitably, makes it into the inner airlock, then into the habitat. Over time, dust accumulates inside your living space. That study by Wang and his team emphasized this exact problem. Martian dust will infiltrate your habitat no matter how careful you are, so you're breathing it. In small quantities, yes, but continuously, day after day, month after month. Those silica particles, those perchlorates, those iron oxides, they're accumulating in your lungs. You develop a cough. Is it just irritation, or is it the beginning of something worse? There's no hospital on Mars. There's a medical bay with basic equipment and whatever pharmaceutical supplies you brought from Earth. If you develop cancer, if you need surgery, if you have a medical emergency beyond what your crew medic can handle, you die. The isolation is total, the risks are omnipresent. And yet, despite all of this, humans will go to Mars. Some already volunteer knowing the dangers. Why? Because we're explorers. Because pushing boundaries is fundamental to who we are as a species. Because the potential rewards, both scientific and philosophical, are profound, but we need to go in with open eyes. Let's talk about what makes Mars scientifically invaluable, because understanding that helps us appreciate both why we must go and why we must be so careful when we do. Mars is a geological time capsule. Earth's surface is constantly recycled through plate tectonics. Old crust gets pushed back into the mantle, melted and reformed. Earth has weather, erosion, biological activity that transforms landscapes. Most of Earth's ancient surface is gone, overwritten by billions of years of geological activity. Mars has no plate tectonics. Its crust is static. Geological features that formed billions of years ago are still there, preserved under a thin blanket of dust. The surface of Mars is like a cosmic archaeological site, where we can literally walk on terrain that dates back to the solar system's youth. Olympus Mons, the largest volcano in the solar system, rises 21 kilometers above the surrounding plains, nearly 2.5 times the height of Mount Everest. It's approximately 374,000 square kilometers at its base. This monster formed over billions of years through repeated eruptions. On Earth, plate tectonics would have carried the volcanic hotspot away, creating chains of volcanic islands like Hawaii. On Mars, the crust stayed put, allowing magma to pile up into this colossal structure. Valles Marineris, the grandest canyon in the solar system, stretches 4,000 kilometers long, 200 kilometers wide, and up to 7 kilometers deep. If you placed it on Earth, it would span the entire continental United States from coast to coast. This isn't just erosion, it's a gigantic rift system that formed when Mars's surface split apart. Why did it split? What internal forces were powerful enough to tear the crust? We don't fully know. Going there, studying the exposed rock layers, analyzing the chemistry, that could tell us fundamental things about how rocky planets evolve. And then there's the question that drives so much of Mars exploration. Did life ever exist there? We know Mars once had liquid water. We know it had a thicker atmosphere. We know that wherever we find liquid water on Earth, no matter how extreme the environment, whether it's boiling hot springs or deep ocean vents or frigid Antarctic lakes, we find life. Life on Earth is tenacious, adaptable, almost unstoppable. If Mars had similar conditions billions of years ago, could life have emerged there too? And if it did, what happened to it when Mars lost its atmosphere and water? Could it have retreated underground? Could it still be there, clinging to existence in subsurface aquifers or pockets of ice? NASA's Perseverance rover is currently collecting samples from Jezero Crater, an ancient lake bed where water once flowed in and out through channels that are still visible from orbit. Those samples, carefully sealed and cached, are waiting for a future sample return mission to bring them back to Earth. When we analyze them in laboratories with equipment far more sophisticated than anything we can send to Mars, we might find organic molecules, biosignatures, maybe even fossilized microbes. Discovering that life arose independently on Mars would be one of the most profound findings in human history. It would tell us that life isn't a fluke, that the universe isn't barren, that wherever conditions are right, life emerges. It would transform our understanding of our place in the cosmos. But here's the ethical dilemma. If Martian life exists, even just microbial life clinging to existence underground, what right do we have to colonize Mars? What right do we have to bring Earth microbes that could contaminate and potentially destroy a biosphere that evolved independently over billions of years? Planetary protection protocols exist for exactly this reason. Every spacecraft sent to Mars is carefully sterilized to avoid forward contamination, bringing Earth life to Mars. And there are protocols for backward contamination too, preventing any potential Martian organisms from reaching Earth. These protocols recognize that we're not just exploring Mars for ourselves. We're stewards of a potentially living world. This adds another layer to the terror of living on Mars. You're not just fighting to survive, you're responsible for not contaminating an entire planet. Every time you go outside, every time you work with Martian soil, every time you return to the habitat, you could be transferring microbes. Earth life is aggressive. If even a few hardy extremophiles survive the journey and find a habitable niche on Mars, they could spread. We could inadvertently destroy the very thing we came to find. The flip side is equally concerning. What if there are Martian microbes, and they're dangerous to us? What if they're biochemically compatible enough with Earth life to infect us but different enough that our immune systems can't fight them? It sounds like science fiction, the Andromeda Strain or War of the Worlds, but it's a real consideration. Before we bring Martian samples back to Earth, they'll be kept in biosafety level 4 containment, the highest level, the same used for Ebola and other deadly pathogens. We're not just exploring a new continent, we're potentially making first contact with an alien biosphere. The stakes couldn't be higher. Now let's address something that might seem mundane, but is actually one of the most significant challenges to long-term Mars habitation: food. You cannot survive on supply shipments from Earth indefinitely. The transit time is 6 to 9 months depending on orbital positions, and launch windows only open every 26 months when Earth and Mars align favorably. If your food production fails, if your crops die, if something contaminates your supplies, you can't just order more. You wait 2 years for the next shipment, assuming anyone on Earth even knows you're in trouble and can organize a rescue mission in time. You need to grow food on Mars. That means agriculture in Martian regolith. Remember those perchlorates we discussed? They're in the soil. You need to wash them out repeatedly before you can plant anything. That requires water, and water on Mars is precious. You can extract it from subsurface ice deposits, but mining ice requires energy, melting it requires energy, purifying it requires energy. Energy on Mars comes from solar panels that get covered in dust, or nuclear reactors that require uranium fuel and sophisticated maintenance. Then there's the question of nutrients. Earth soil is rich in organic matter, decomposed plants and animals, microorganisms that break down nutrients and make them available to roots. Martian regolith is sterile. It's never supported life. It's mineral dust. You need to add nutrients artificially. Nitrogen, phosphorus, potassium, trace elements. Where do those come from? You either bring them from Earth, expensive, limited, or you create them from Martian resources through industrial processes that require energy and sophisticated chemistry, and you need to do all of this inside pressurized greenhouses. Plants need carbon dioxide. Mars has plenty of that in its thin atmosphere, but they also need the right temperature, the right humidity, protection from radiation. Your greenhouse needs to be airtight, climate-controlled and shielded. Scientists at the International Potato Center and NASA have run experiments growing potatoes in Martian regolith simulants. It works barely under carefully controlled conditions, but scaling that up to feed a crew of 6 people for years, that requires greenhouses covering hundreds of square meters, sophisticated automation, constant monitoring, a single blight, a single pest that somehow makes it to Mars in cargo, a fungal infection. Any of these could wipe out your entire food supply. And unlike Earth, where crop failures in one region can be compensated by imports from elsewhere, on Mars there is no elsewhere. Your settlement is all there is. Some proposals suggest bringing insects for pollination and decomposition, bees, earthworms, composting beetles. But now you're not just managing crops, you're managing entire miniature ecosystems. Ecosystems are complex, interconnected, fragile. They require balance. Too many of one species, a disease outbreak, an unforeseen interaction, collapse cascades through the system. You thought staying alive on Mars was just about radiation shielding and dust filtration. No, it's about becoming a master gardener, a genetic engineer, an ecosystem manager, all while living in a hostile environment where every mistake is potentially fatal. Let me share something that doesn't get discussed enough: the genetic implications of long-term Mars habitation. Humans evolved under Earth's gravity, Earth's radiation levels, Earth's day-night cycles. Our bodies are finely tuned to these conditions. Put humans in radically different conditions for extended periods, and physiology changes, not just for individuals, but potentially for future generations. Astronauts on the International Space Station in microgravity for 6 months to a year experience bone density loss, muscle atrophy, vision problems from increased intracranial pressure, immune system dysfunction. These are somewhat reversible with exercise and after returning to Earth's gravity. But Mars isn't microgravity, it's 38% gravity. Nobody knows what living in 38% gravity for years does to human physiology. Will children born on Mars develop normally? Their bones, adapted to lower gravity, might become less dense. Their muscles might develop differently. Could someone born on Mars ever visit Earth? The 3 times greater gravity might be crushing, potentially dangerous. And then there's radiation. Chronic radiation exposure causes DNA damage. Some of that damage gets repaired, but some accumulates. Mutations occur. Most mutations are harmless or harmful to the individual, but some might be passed on to offspring. Over generations, are we looking at increased cancer rates, genetic disorders, shortened lifespans? There are no easy answers because we have no data. No human has ever lived on Mars. No human has ever tried to raise children in partial gravity under constant radiation. We're contemplating an experiment with human subjects where we don't know the outcomes and can't easily reverse the consequences. This raises profound ethical questions. Do we have the right to subject people, especially children who have no choice in the matter, to these unknown risks, or is the expansion of humanity into the cosmos worth those risks? Different people will answer those questions differently, and there's no objective right answer. But we need to ask them before we send permanent settlers, before we establish colonies, before we create a situation where people are committed to Mars with no possibility of return. Let's shift gears and talk about something equally critical: water. Mars isn't completely dry. We know there's water ice at the poles, vast deposits that, if melted, could theoretically cover the planet in liquid dozens of meters deep. We know there's subsurface ice at higher latitudes, detected by radar instruments on orbiting spacecraft. We've seen evidence of briny water seeping down crater walls during Martian summers, though that's still debated. But here's the problem. Accessing water on Mars is difficult and energy-intensive. Polar ice is mixed with frozen carbon dioxide, dry ice. You need to separate water ice from dry ice, which requires heating to specific temperatures. Polar regions are also extremely cold. Winter temperatures drop below -125 degrees Celsius and dark for extended periods. Operating machinery in those conditions is nightmarish. Subsurface ice deposits at lower latitudes are more accessible, but you need to dig. Mars rovers have shown that digging on Mars isn't trivial. The regolith can be surprisingly hard in places, almost concrete-like from cementing processes. You need excavation equipment, drills, scoops, bulldozers, all of which must function in extreme cold, dusty conditions with minimal maintenance. Once you extract ice, you need to melt it. That requires energy. Then you need to purify it because Martian ice probably contains dissolved salts, perchlorates, and other contaminants. Purification requires filtration systems, chemical treatment, more energy. Water on Mars isn't like turning on a tap. It's an industrial process that never stops because you're constantly losing water. Life support systems aren't 100% efficient. Some water escapes as vapor and needs to be recaptured. Plants transpire water that must be recycled. Humans produce waste that contains water, even with 95% recycling efficiency, which is optimistic. You're losing 5% continuously. You need to mine more ice to compensate, and water isn't just for drinking and growing food. You need it for radiation shielding. Water is one of the best materials for blocking radiation. Hydrogen atoms in water molecules are excellent at absorbing energetic particles. Many Mars habitat designs propose surrounding living quarters with water tanks that serve double duty: water storage and radiation shield. But now your radiation protection is also your life support. If something goes wrong with your water storage, you lose both. Then there's the question of where you land, where you build your base. This isn't arbitrary. Location determines survival. You need to be near water ice deposits for the reasons we just discussed. You need to be at relatively low elevation, where atmospheric pressure is slightly higher. Mars's thin atmosphere is even thinner at high elevations. Olympus Mons, at 21 kilometers altitude, has effectively no atmosphere. Landing there would be suicidal. You want to be near the equator for warmer temperatures and more consistent sunlight for solar power. But equatorial regions have less accessible water ice. Higher latitudes have more ice, but are colder and receive less sunlight, especially during winter when the sun barely rises above the horizon for months. You want flat terrain for landing and construction. But flat terrain might lack geological diversity. You came to Mars to do science, remember? You want access to interesting rock formations, ancient lake beds, sites that might preserve biosignatures. Every location is a compromise, and once you choose, you're committed. You can't easily move. Relocating a Mars base would mean rebuilding everything from scratch. NASA and other space agencies have identified potential landing sites through years of orbital reconnaissance. Jezero crater, where Perseverance is currently exploring, is one. Oxia Planum, the target for the European Space Agency's Rosalind Franklin rover, is another. These sites balance scientific interest with practical considerations, relatively flat landing zones, evidence of past water, accessible from an engineering standpoint. But accessible on Mars is relative. Everything is hard, everything is dangerous. Now let's talk about something that keeps engineers awake at night. Mechanical failure. On Earth, when something breaks, you order a replacement part. It arrives in days. On Mars, the nearest parts supplier is 6 to 9 months away, and only if a spacecraft happens to be heading to Mars during the current launch window. If you need something urgently and no mission is scheduled, you're out of luck. You wait 26 months for the next window, then another 6 to 9 months for transit. You're looking at 3 years minimum. This means every critical system needs multiple redundancies. You need backup life support systems, backup power generation, backup water purification, backup communication equipment. All of those backups add mass, which makes the mission more expensive, which limits how much other equipment you can bring, and you need spare parts, lots of them, but you can't predict every possible failure mode. Engineers try. They run failure mode analysis. They stress test components. They design for redundancy. But unexpected things happen. A seal degrades faster than anticipated because Martian dust is more abrasive than predicted. A solar panel develops a short because of electrostatic buildup. A pump fails because lubricants behave differently in low pressure and temperature extremes. The International Space Station deals with this through regular resupply missions, several per year. Parts break, new ones arrive. Astronauts conduct spacewalks to replace faulty equipment. It's routine. Mars can't be resupplied regularly. You need to fix things with what you have. That means three-dimensional printing becomes crucial. Instead of bringing every possible spare part, you bring raw materials and printers capable of manufacturing parts on demand. NASA has already tested three-dimensional printers on the ISS. They work, mostly. But printing complex mechanical parts with tight tolerances in Martian conditions, that's cutting-edge technology we're still developing, and some things can't be printed. Electronics, for instance, microchips, computers. If your main computer fails and you don't have a spare, you're in catastrophic trouble. Computers control life support, power management, communication, everything. You absolutely need backups. But computers are sensitive to radiation. Cosmic rays can cause bit flips, random errors in memory that corrupt data or cause malfunctions. Spacecraft use radiation-hardened computers designed to withstand this, but they're expensive, heavy, and often less powerful than commercial equivalents. You're trying to run a sophisticated Mars base with computers that are years behind current Earth technology because those are the only ones tough enough to survive the environment. And if they fail despite being radiation hardened, you're dependent on backups. If those fail, you're manually controlling systems designed to be automated. Human error skyrockets. Accidents happen. Let's discuss a scenario that emergency planners dread. Medical emergencies. You're on Mars with a crew of 6. One of you is trained as a medic, maybe a doctor or a paramedic with extensive training in emergency medicine, surgery, dentistry. But you're not a specialist in everything. Nobody is. Someone develops appendicitis. On Earth, that's a routine surgery. On Mars, you need to perform an appendectomy in your small medical bay with limited equipment, no specialists to consult in real time, and the knowledge that if something goes wrong during surgery, If the patient hemorrhages, develops an infection, goes into shock, your options are limited, or someone breaks a bone. In 38% gravity, fractures might be different from Earth fractures. Healing might proceed differently. Do you have the right equipment for setting bones, for immobilizing limbs? What if it doesn't heal properly? What if complications arise? Radiation-induced cancers might not manifest immediately, but over years, your crew's cancer risk climbs steadily. If someone develops cancer, what are your options? You don't have chemotherapy drugs. They have limited shelf lives and require refrigeration. You don't have radiation therapy equipment. You certainly can't perform complex surgeries to remove tumors. The patient faces a death sentence unless an emergency return mission can be organized, which takes years to plan and execute. Psychological crises are perhaps even more concerning because they're harder to predict and treat. Depression, anxiety, panic attacks, psychotic breaks, all are possible under extreme stress and isolation. Your medic has psychiatric medications, but what if someone becomes actively suicidal? What if interpersonal conflicts escalate to violence? On Earth, we separate people in crisis, bring in counselors, sometimes hospitalize patients. On Mars, you're locked together in a small habitat. There's nowhere to go. If someone becomes a danger to themselves or others, your options are horrifyingly limited. Sedation, physical restraint. These are extreme measures with ethical implications and practical risks. NASA screens astronauts extensively for psychological resilience, but screening isn't perfect, and nobody truly knows how they'll respond until they're actually in the situation. The famous Mars 500 simulation, where 6 volunteers spent 520 days in isolation in a mock spacecraft, revealed interpersonal tensions, motivation problems, sleep disorders. And those participants knew it was a simulation. They knew they could leave in an emergency. Mars colonists won't have that safety net. The psychological dimension of Mars colonization might be the most underestimated challenge we face. You can engineer solutions to radiation, dust, temperature extremes. You can design better life support systems and habitats. But human psychology? That's far harder to engineer around. Let me share something that doesn't get enough attention. The sheer monotony of Mars. Yes, you're on another planet. Yes, the landscape is alien and scientifically fascinating, but after weeks, months, years, it's just rocks and dust, always rust-colored, always barren, no plants, no animals, no weather beyond dust storms, no seasons beyond temperature changes and shifting carbon dioxide ice. On Earth, even in extreme environments like Antarctica or the deep ocean, there's life. Penguins, seals, fish, plankton. Life provides stimulation, variety, connection to the biological world we evolved in. Mars has none of that. It's a sterile, static museum of geology. You can't go hiking without a spacesuit and extensive planning. You can't sit outside and watch clouds drift by. You can't feel rain or smell flowers or hear birdsong. Every single sensory experience that connects humans to the natural world is absent. Entertainment becomes crucial for psychological survival. You bring books, movies, music, games, but storage is limited. Bandwidth for downloading new content from Earth is limited. Deep space communication is measured in kilobits per second, not megabits. Downloading a single high-definition movie could take days. You talk to your crewmates, but they're the same 6 people you've been living with for years. Every story has been told. Every joke has been heard. Interpersonal dynamics become crucial and dangerous. Small annoyances magnify into conflicts. Someone's chewing habits become unbearable. Someone's work ethic is frustrating. These tiny frictions on Earth would be relieved by going home, seeing other people, having space. On Mars, there is no relief. Some propose virtual reality as a solution. Let people experience Earth environments virtually, but VR requires equipment that can fail. And there's something psychologically challenging about knowing that the forest you're walking through is fake, while outside your habitat is endless desolation. We need to think carefully about who we send to Mars. Not just their technical skills, but their psychological makeup, their ability to find meaning and purpose in isolation, their resilience in the face of monotony and danger. We might be selecting for a particular type of human temperament, people who find fulfillment in introspection, who don't need constant external stimulation, who can maintain motivation without immediate rewards. But here's the paradox. Those same traits might make someone less effective at interpersonal communication, less adaptable to group dynamics, potentially more isolated. You need people who are simultaneously independent and collaborative, introspective and socially skilled, risk-tolerant and cautious. That's a narrow psychological profile, and even then, there are no guarantees. Let's talk about something that sounds like science fiction, but is a real consideration. The point of no return. When you commit to going to Mars, you're making a calculation about whether you'll ever come back. The delta V, the change in velocity required, to go from Mars' surface to Earth is substantial. You need a rocket capable of launching from Mars, which means you either bring that rocket with you from Earth or you manufacture fuel on Mars. In situ resource utilization, making fuel from Martian resources, is the only practical option for return missions. The most discussed approach is the Sabatier reaction, combining carbon dioxide from Mars's atmosphere with hydrogen to produce methane and water. Methane and oxygen, which you separate from water or extract from the atmosphere, can fuel rockets. SpaceX's Starship is designed around this concept. The idea is to land on Mars with empty fuel tanks, set up chemical plants that produce methane and oxygen over months, then refuel for the return journey. It's elegant in theory, but it requires everything to work perfectly. Your chemical plant needs power, lots of it. Your processing equipment can't fail. You need time, months to years, to produce enough fuel. If any step fails, if you can't manufacture sufficient fuel, you're stranded. And even if you successfully produce fuel, launching from Mars is risky. There's no mission control to guide you through launch. There are no emergency landing sites if something goes wrong. You lift off or you crash. If you crash, rescue is impossible. So the first Mars settlers face a stark reality. Going to Mars might be permanent. Not by choice necessarily, but because the return option is so uncertain. You're committing to spending the rest of your life, however long that is, on another world. Some people romanticize this. They talk about pioneering, about the settlers who colonized the Americas or Pacific Islands, knowing they'd never return home. But those pioneers went to places with air and water and food. They went to places where, despite the dangers, the environment was fundamentally compatible with human life. Mars is not compatible with human life. Every single moment of every single day, the planet is actively trying to kill you. There's no moment of peace, no moment where you can let your guard down. Even in sleep, you're dependent on machines keeping you alive. The psychological weight of permanence is crushing. You'll never see Earth again. Never breathe unfiltered air. Never swim in an ocean. Never feel rain. Never see a forest or hear thunder or smell flowers after a spring rain. All of those sensory experiences that define human existence, gone forever. And if you have children on Mars, they'll never experience those things at all. They'll grow up in a world of metal and plastic and rock, where outside is death and Earth is just a bright blue dot in the sky, a place their parents tell stories about, but that they can never visit because their bodies, adapted to Martian gravity, might not survive Earth's pull. Is that fair to them? Do we have the right to create human beings who will spend their entire lives imprisoned on a hostile world? Or is giving them life even under those constraints better than not existing at all? These aren't abstract philosophical questions. They're real dilemmas that Mars colonization forces us to confront. Now let's address the economic reality of Mars colonization, because this determines whether it happens at all. Going to Mars is staggeringly expensive. NASA's Apollo program, which sent 12 humans to the moon's surface between 1969 and 1972, cost approximately $25 billion in 1973 dollars. Adjusted for inflation, that's roughly $280 billion in today's money, and the moon is close, 3 days away. Missions lasted days to weeks, not years. Mars missions are far more complex and expensive. Estimates for a single crewed Mars mission range from $100 billion to $500 billion, depending on architecture and assumptions. And that's for a mission, landing, staying for a few months, returning. Establishing a permanent settlement, multiply that by factors we can only guess at. Who pays for this? Government space agencies? NASA's current annual budget is around $25 billion. The European Space Agency gets roughly €7 billion annually. These budgets support numerous missions and programs. Redirecting enough funding to support Mars colonization would require cutting other programs or massive budget increases that require political will. Private companies like SpaceX claim they can do it cheaper through reusable rockets and innovative engineering. Elon Musk has stated his goal of making Mars colonization affordable, eventually bringing costs down to where hundreds of thousands or millions of people could go. But SpaceX is still developing the technology. Starship hasn't yet reached orbit, let alone Mars. The technical challenges remain immense, and even if SpaceX succeeds in dramatically lowering launch costs, that's just transportation. What about the habitats, the life support systems, the power generation, the food production, the medical equipment, the tools and spare parts and everything else needed to keep people alive for years? Those costs don't disappear because your rocket is reusable. Some propose that Mars colonization could become economically self-sustaining through resource extraction. Mars has minerals, metals, potentially valuable isotopes. Could Mars become an exporter, shipping valuable resources back to Earth or to space-based industries? The problem is return economics. Lifting anything from Mars's surface to orbit is expensive in terms of energy and fuel. You'd need to find resources valuable enough to justify that expense. On Earth, we mine gold and platinum because they're worth thousands of dollars per ounce. What's on Mars that's worth not thousands but tens of thousands or millions of dollars per kilogram to justify the transport costs? Some suggest deuterium, a hydrogen isotope useful for fusion reactors, if we ever get fusion working commercially. Some suggest rare earth elements, but Earth has those too, and mining them on Earth, even from difficult locations, is vastly cheaper than mining on Mars. The harsh reality is that Mars probably can't be economically self-sustaining in any time frame we can predict. It will be subsidized either by governments or by wealthy benefactors who see non-economic value in establishing humanity as a multi-planetary species. That raises sustainability questions. What happens if political priorities shift? If funding dries up? If the billionaire backing the colony loses interest or goes bankrupt? Do the colonists just die? Can you ethically abandon people on Mars? These are not hypothetical scenarios. History is full of colonies that failed when support from home dried up. The difference is that failed Earth colonies could sometimes integrate with local populations or survive by adapting to local conditions. A failed Mars colony just dies. There's no alternative. Let's discuss the timeline question. When could this actually happen? SpaceX is targeting the 2030s for crewed Mars missions. NASA's Moon to Mars program plans for crewed Mars orbit missions in the late 2030s, with surface landings potentially in the 2040s. China has announced ambitions for crewed Mars missions by 2045 to 2050. These timelines are optimistic. They assume technical development proceeds smoothly, funding remains consistent, no major setbacks occur. History suggests we should add years or decades to these estimates. The space shuttle was supposed to fly weekly and make space access routine. It never came close. The International Space Station took far longer to build and cost far more than initial projections. But let's say we're optimistic. Let's say humans land on Mars in the 2030s or 2040s. That's still a mission. Landing, exploring, returning, that's not colonization. Building permanent settlements capable of sustaining hundreds or thousands of people. We're talking late 21st century at the earliest, possibly 22nd century. Current young adults might live to see the first humans walk on Mars. But true colonization, cities on Mars, children being born and raised there, self-sustaining infrastructure, that's for future generations. If it happens at all, and there's legitimate debate about whether it should happen, not everyone agrees that Mars colonization is desirable or ethical. Some argue we should focus on Earth. We have immense problems here: climate change, poverty, inequality, biodiversity loss. Shouldn't we fix our home planet before we try to colonize another? Every dollar spent on Mars is a dollar not spent on Earth's problems. Others counter that this isn't either or. The technologies developed for Mars, life support recycling, renewable energy, efficient food production, can benefit Earth, and making humanity multi-planetary is insurance against existential risks. A single planet means a single point of failure. An asteroid impact, nuclear war, pandemic, artificial intelligence gone wrong, any of these could end human civilization if we're only on Earth. Multiple planets mean humanity survives even if one planet fails. But critics point out that Mars is a terrible insurance policy. It's harder to live on Mars than to recover from almost any Earth catastrophe. Even after nuclear war, Earth would still have breathable air, drinkable water, edible plants. Rebuilding on post-apocalyptic Earth would be vastly easier than maintaining civilization on Mars. There's also the perspective that the money and effort going into Mars colonization represents a kind of escapism. Wealthy elites building themselves a backup plan while the rest of humanity struggles. If Earth becomes uninhabitable for most people, only the rich could afford to leave. That's not inspiring, that's dystopian. These debates matter because they shape policy, funding, public support. Mars colonization won't happen without sustained commitment from governments, corporations, and societies. If we collectively decide it's not worth it, it won't happen, regardless of technical feasibility. My own perspective, and I want to be transparent about this, is that Mars exploration is scientifically invaluable. Going to Mars, studying it, searching for evidence of past or present life, understanding its geology and climate history, that expands human knowledge in profound ways. That's worth doing, but colonization is different from exploration. Establishing permanent settlements raises ethical, practical, and philosophical questions that don't have clear answers. We should proceed thoughtfully, carefully, with humility about what we don't know and respect for what we might find. Let's talk about something that often gets overlooked in discussions of Mars colonization: governance and law. Who makes the rules on Mars? Who enforces them? What legal framework applies when humans from different nations, corporations, and backgrounds are living together on another planet? The Outer Space Treaty of 1967, signed by over 100 countries including all major spacefaring nations, establishes some basic principles. No nation can claim sovereignty over celestial bodies. Space exploration must benefit all humankind. Weapons of mass destruction are banned in space. Nations are responsible for their space activities, whether conducted by governments or private entities. But the Outer Space Treaty was written during the Cold War, focused on preventing military conflict in space and ensuring the moon wouldn't be claimed by superpowers. It wasn't designed for colonization scenarios. If SpaceX establishes a settlement on Mars, who governs it? Is it under US jurisdiction because SpaceX is an American company? What if the settlers include people from dozens of countries? What if China establishes a separate settlement 50 kilometers away? Are there now effectively two separate jurisdictions on Mars? What laws apply? Criminal law, property rights, contracts, family law, all of these developed within terrestrial legal systems rooted in specific cultures and histories. Do those systems simply extend to Mars, or does Mars need its own legal framework? Consider a scenario. Two settlers have a dispute over resource allocation. One accuses the other of taking more than their fair share of water rations. How is this resolved? Is there a court, a judge, a jury of their peers, which on a settlement of 6 people means your crewmates, people you live and work with every day, must sit in judgment? That creates impossible social dynamics, or worse, someone commits a serious crime, theft, assault, even murder. What's the punishment? There are no prisons on Mars. You can't afford to imprison someone. That requires resources, space, guards. Do you confine them to their quarters? For how long? What if they're needed for critical work? You're a crew of 6 and everyone has essential duties. Can you function if one person is imprisoned? Execution. That's ethically problematic and legally banned in many jurisdictions. But what's the alternative if someone becomes a clear and present danger to the survival of the settlement? Exile? Where do they go? Outside without a suit is immediate death. That's execution by another name. Give them a suit and kick them out. They die slightly more slowly. There's nowhere to send them. These aren't academic questions. Small, isolated communities throughout history have struggled with justice and governance. Antarctic research stations, the closest Earth analogy to Mars bases, operate under frameworks where participants agree to abide by certain rules and return to their home countries for serious legal issues. But Antarctic stations can be evacuated. Mars settlements can't. Some propose that Mars settlements will develop their own governance systems organically. Communities will establish rules collectively, evolving systems that work for their specific circumstances. That's possible, but it's also risky. Small communities under extreme stress can develop toxic dynamics. Charismatic individuals can accumulate power. Scapegoating and authoritarianism can emerge. There's also the question of property rights. Who owns the water ice you extract? Who owns the habitat you build? The Outer Space Treaty says no nation can claim territory, but it doesn't explicitly address whether individuals or corporations can own property or extract resources. The Artemis Accords, a more recent international agreement led by NASA, attempt to address this by establishing safety zones where activities can occur without interference and affirming the right to extract and use space resources. But the accords are controversial. Major spacefaring nations like China and Russia haven't signed. Critics argue the accords are effectively privatizing space resources in violation of the spirit of the Outer Space Treaty. If different nations and corporations establish competing settlements on Mars with different legal frameworks and resource claims, we could be setting up future conflicts. Resource disputes on Earth have triggered wars. What happens when settlements disagree over who has rights to a critical water ice deposit? You might think warfare on Mars is implausible. Settlements would be too dependent on cooperation for survival. But humans have fought wars in defiance of rational self-interest throughout history. Ideology, nationalism, resource competition, grievances, these can override pragmatic concerns. And on Mars, where resources are so scarce and survival margins so thin, conflicts could be especially intense. Then there's the question of reproduction and children's rights. If a child is born on Mars, what is their citizenship? Are they citizens of their parents' home countries? Citizens of Mars, which isn't a country and has no government? What if their parents are from different nations? More fundamentally, do children born on Mars have the right to experience Earth? Their bodies, developed in Martian gravity, might not tolerate Earth's gravity. They might be physically unable to visit the planet where humanity evolved, where most humans live, where their extended family resides. Is that a form of imprisonment? Have we created a new class of humans, Martians, who are fundamentally separated from Earthborn humans? And what about reproductive rights on Mars? In a small settlement where resources are tightly constrained, can people have children freely? Or does the community need to regulate reproduction to ensure population doesn't exceed life support capacity? That's a dystopian scenario, reproductive control by committee, but it might be necessary for survival. These questions become even more complex when considering genetic engineering. If we know that certain genetic modifications could help humans tolerate radiation better or adapt to lower gravity, do we have an obligation to genetically modify Mars colonists and their children? Or is that crossing an ethical line, engineering humans for specific environments? The more you examine the details of Mars colonization, the more you realize we're not just talking about engineering and logistics. We're talking about reimagining human society, law, ethics, rights, and governance in an entirely new context. Let's shift to something more immediate, the psychology of the journey. Before you even reach Mars, you spend 6 to 9 months in a spacecraft. You're confined to a small volume with a handful of other people. There's no privacy. Every conversation can be overheard. Every habit, how someone eats, sleeps, talks, breathes, becomes magnified in the enforced intimacy. You're moving away from Earth at thousands of kilometers per hour. Earth becomes smaller in the window until it's just another point of light. The sun looks slightly smaller. Space is black and empty and vast beyond human comprehension. There's a phenomenon called the overview effect. The astronauts who've seen Earth from space often describe profound shifts in perspective, a sense of Earth's fragility and unity, a feeling that national boundaries are arbitrary and meaningless from that vantage point. It can be positive, but it can also be destabilizing. Some astronauts have reported feelings of depression and disconnection after seeing how small and isolated Earth appears in the void. Now imagine that feeling intensifying over months as Earth recedes further and further, becoming indistinguishable from stars. You're heading toward Mars, which is just a reddish dot, growing slowly larger. No blue, no green, no white clouds, just rust and rock. You can communicate with Earth, but there's increasing delay. At minimum distance, Mars is about 3 light minutes from Earth. Signals take 3 minutes to reach Earth and 3 minutes to return, so even a simple question and answer exchange has a 6-minute delay. As Mars and Earth move in their orbits, that delay increases. At maximum distance, the delay can be over 20 minutes each way. Real-time conversation becomes impossible. You send a message and wait 40 minutes for a response. That's not a conversation, that's an asynchronous exchange. The psychological impact of that communication lag is significant. On the ISS, astronauts can call home with only slight delays. Communication feels normal. On the way to Mars, every interaction with loved ones is stilted, disconnected. And you know that once you land on Mars, that delay persists forever. Every conversation with family, friends, anyone on Earth, there's always that gulf cup of time and space between you. You can't call someone in a crisis and get immediate support. You can't have a spontaneous conversation. Every exchange requires patience and planning. Some crew members might handle this well. Others might spiral into depression or anxiety. And remember, you're monitoring each other constantly during the journey because crew dynamics are mission critical. If someone starts showing signs of psychological distress, what do? You're months from Earth. months from Mars. You're in transit with no possibility of abort or rescue. You have psychiatric medications in the medical kit, but those are last resorts with side effects and limited supplies. You have counseling protocols, crew members trained in psychological support techniques. But you're not professionals, and the person in crisis is your colleague, friend, person you depend on for survival. The journey to Mars might be the most psychologically challenging part of the entire mission. At least on Mars you have tasks, science, construction, maintenance, purpose and distraction. During transit, you're just waiting, confined, moving through the void toward an uncertain future. Entertainment becomes critical, but you can only watch so many movies, read so many books, play so many games before the monotony sets in. Some crews might handle it through rigorous schedules, structured days with exercise, work tasks, education, recreation. Others might struggle with motivation in the absence of immediate challenges, and there are physical challenges during transit. Microgravity or very low gravity, if your spacecraft is rotating for artificial gravity, causes the same bone density loss and muscle atrophy astronauts experience on the ISS. You exercise rigorously, but it's never quite enough. By the time you reach Mars, you're weakened, then you have to land. And Mars landings are terrifying. Mars has enough atmosphere to cause problems, but not enough to help much. Entry, descent, and landing, EDL in aerospace terminology, is called 7 minutes of terror for robotic missions. For crewed missions, it's even more challenging because you're landing something much heavier, habitats, life support people. You're entering Mars's atmosphere at thousands of kilometers per hour. Friction generates heat. Your heat shield glows red hot. G-forces slam you back in your seat. You deploy parachutes, but Mars's thin atmosphere means parachutes alone can't slow you enough. You fire retro rockets at the last moment, burning fuel you manufactured or brought with you, hoping your calculations are correct. And you're doing all of this autonomously. The communication delay means Earth can't help. By the time mission control on Earth sees telemetry showing you've entered the atmosphere, you've already landed or crashed. You're on your own, trusting in engineering and hoping nothing goes wrong. Robotic landers have about a 50% success rate historically. Crewed missions will be more robust, more redundant, more carefully designed, but the risks remain. You could crash, systems could fail, you could land off target, kilometers from your pre-positioned supplies. And once you land, there's no going back immediately. You're committed to surface operations, months or years depending on mission architecture, before the next launch window opens for return. Let's talk about what happens after landing, the actual work of living on Mars. Your first tasks are survival basics. Verify habitat integrity, confirm life support is functioning, check power systems, assess landing accuracy and condition of equipment. This all happens under immense stress. You've just endured months of space travel and a harrowing landing. You're physically weakened, psychologically drained, and now you need to perform critical technical work flawlessly because mistakes are fatal. If you landed near pre-positioned cargo, supplies sent ahead on earlier missions, you need to locate it, verify it survived landing and the intervening months or years on the surface, and transport it to your habitat. That means operating rovers or other vehicles in Martian conditions, which you've trained for but never actually done under real conditions. Everything takes longer than planned. Murphy's Law operates with particular cruelty on Mars. A seal doesn't fit quite right because thermal expansion in Martian temperatures differs from predictions. A connector is jammed with dust. A battery didn't charge as expected because solar panel efficiency was slightly lower than models predicted. You troubleshoot, improvise, work around problems. This is where crew selection becomes crucial. You need people who stay calm under pressure, who can solve problems creatively with limited resources, who don't panic when things go wrong, and things will go wrong, constantly. One of the fundamental challenges of Mars is that you're operating at the edge of human capabilities with no margin for error. On Earth, most systems have substantial safety margins. Buildings are designed to withstand forces far beyond what they'll normally experience. Vehicles have redundant safety systems. Infrastructure is overbuilt because the cost of failure is high, but not catastrophic. On Mars, mass is precious. Every kilogram you bring from Earth costs thousands of dollars, possibly tens of thousands depending on mission architecture. So you can't overbuild, you can't bring excessive spares. You design to the minimum safety margins you can justify, which means you're operating closer to failure points. This creates constant stress. You're always aware that systems are running near their limits, that there's little buffer if something goes wrong. It's like driving a car where you know the brakes are functional but have minimal stopping distance. Technically safe, but psychologically taxing. Now let's discuss one of the most mundane but critical aspects of Mars life: hygiene. Water is precious. You can't shower like on Earth. You can't afford to use tens of liters of water for washing. Astronauts on the ISS use wet wipes and dry shampoo. They take sponge baths with minimal water, carefully capturing every drop for recycling. On Mars, it's similar. You might get to shower once a week with strictly rationed water, perhaps a few liters total, which needs to be captured and recycled. The rest of the time you're using wipes, dry shampoo, deodorant. You smell. Everyone smells. The habitat smells. Recycled air carries odors. Human bodies, food, equipment, the faint chemical scent of life support systems. You become noseblind to it, but it's there. Visitors from Earth, if there ever are any, would probably find it unpleasant. Laundry is similar. You can't wash clothes frequently. Water and energy are too precious. So you wear clothes multiple times before washing. Socks, underwear. You might get fresh ones every few days rather than daily. Outer clothes might be worn for weeks between washes. This isn't just uncomfortable, it has health implications. Skin infections can develop in unhygienic conditions. Fungal infections are particularly problematic in enclosed environments. Your medical supplies include antifungals and antibiotics, but these are limited and some infections are resistant to treatment. And then there's waste management, which sounds trivial but is actually complex and critical. Human waste, urine and feces, contains water and nutrients that need to be recovered. On the ISS, urine is processed into drinkable water. Solid waste is either stored and returned to Earth or loaded into cargo spacecraft that burn up in the atmosphere. On Mars, you need to close the loop more completely. Solid waste needs to be processed to recover water and nutrients. This probably involves composting or incineration, breaking down organic matter to extract useful components. But handling human waste in a spacesuit is challenging. You wear adult diapers for EDVAs, which is uncomfortable and undignified. For longer EVAs, 6 to 8 hours, you're essentially sitting in your own waste for hours. It's unpleasant, it causes skin irritation, and it's psychologically demoralizing. Inside the habitat, you have toilet facilities, but they're not like Earth toilets. Martian toilets use airflow or other mechanisms to handle waste in low gravity and low pressure. They're functional but not comfortable. And if the toilet breaks, which happens even on the ISS, you have a serious problem. Waste management system failures are among the most commonly reported issues on space stations. Let's talk about food in more detail, because this dominates daily life. Initially, Mars settlers eat pre-packaged food brought from Earth, freeze-dried meals, canned goods, food designed for long shelf life. It's nutritionally adequate but monotonous. Astronauts on long missions report craving fresh food intensely. The taste, texture, variety. As quickly as possible, you want to start growing fresh food. This means establishing greenhouses or growth chambers, controlled environments where you grow vegetables, fruits, grains. Plants on Mars need several things: light, water, nutrients, atmosphere, temperature control. Light comes from the sun, supplemented by artificial LED grow lights. Water comes from ice you've mined and purified. Nutrients come from processed Martian soil mixed with organic waste from composting. Atmosphere comes from your life support system. Elevated carbon dioxide helps plants grow faster, but growing plants on Mars is incredibly challenging. Plants are sensitive. They need specific light wavelengths, specific temperatures, specific humidity levels. Too hot or too cold and they die. Wrong humidity and they develop fungal infections or dehydrate. Wrong nutrient balance and they become stunted or diseased. You're essentially becoming farmers, but with no room for failure. If your crop fails, you're back to rationed, pre-packaged food. Multiple failures and you face starvation, and agriculture takes time. Lettuce grows in about a month. Tomatoes take 2 to 3 months. Wheat takes 3 to 4 months. Potatoes, often discussed as a Mars staple crop because they're calorie-dense and relatively hardy, take 3 to 4 months. So from planting to harvest, you're waiting months. If something goes wrong halfway through, you've lost weeks or months of effort and resources. Pests are another concern. You try to prevent bringing insects or pathogens from Earth, but it's nearly impossible to sterilize everything. A few aphids or fungal spores can devastate crops in a closed environment with no natural predators. On Earth, if you lose crops, you buy food. On Mars, there is no store. Your life support timeline becomes critical. How many days of food do you have in reserve? If you're down to 30 days and your next crop won't harvest for 60 days, you're in crisis. Rationing becomes necessary, calories are cut, people lose weight, lose energy, become weaker and more susceptible to illness. Morale plummets, conflicts over food distribution arise. Who gets how much? Are rations equal or based on work performed? These seem like small decisions, but they can tear communities apart. Some missions might bring livestock, chickens for eggs and eventually meat, fish in aquaponic systems, insects like crickets for protein. Each adds complexity. Animals need food, water, space, waste management. They can get sick, they can die. But they provide protein and psychological benefits. Caring for living creatures provides purpose and connection. The goal is to eventually achieve food self-sufficiency, where you produce enough calories to sustain your population without resupply from Earth. But this takes years to establish and remains precarious. One major system failure: greenhouse loses pressure, power failure kills crops, water contamination, and you're back to crisis. Let's discuss another daily reality: exercise. In Martian gravity, 38% of Earth's, your body doesn't work as hard to move around. That sounds convenient, but it's medically problematic. Your bones don't experience normal loading forces, so they lose density. Your muscles don't work against normal resistance, so they atrophy. Your cardiovascular system doesn't pump as hard, so your heart weakens. Astronauts on the ISS exercise 2 to 3 hours per day to counteract microgravity effects. Even with that, they lose bone density and muscle mass. Mars's partial gravity is better than microgravity, but you still need regular exercise, probably an hour or more daily, to maintain health. That means every habitat needs exercise equipment: treadmills, resistance machines, stationary bikes. You need space for this equipment and time in your schedule. After a long day of physically demanding work, EVAs, construction, maintenance, you still need to exercise. It's exhausting. And exercise on Mars is less effective than on Earth because you're not working against full gravity. Running on a treadmill in 38% gravity provides less bone loading than running on Earth. You might need to add weight vests or resistance harnesses to increase the effectiveness. Over years, despite exercise, Mars settlers will likely experience some level of permanent physical changes. Bones become less dense, muscles adapt to lower gravity, the heart becomes less robust. If you ever return to Earth, readaptation would be difficult, perhaps impossible if you've spent decades on Mars. Children born and raised on Mars would face even greater challenges. Their skeletons would develop in low gravity. Their muscles would adapt to Martian conditions. They would be true Martians, adapted to Mars, but potentially unable to ever experience Earth. This raises profound questions about human evolution and divergence. Are we creating a new branch of humanity? Over generations, could Martians and Earth humans become so physiologically different that they're effectively separate subspecies? Let's talk about something that most people don't think about: boredom and purpose. Yes, you're on Mars doing groundbreaking work, but a lot of that work is repetitive maintenance, checking systems, cleaning filters, running diagnostics, repairing equipment, monitoring plant growth, processing waste, recording data. It's important work, but it's not glamorous. Many days are routine: wake up, exercise, eat, work, exercise, personal time, sleep, repeat. The landscape outside doesn't change. The routine doesn't change. Weeks blend into months. Astronauts on the ISS report that maintaining motivation over long missions is challenging. They're selected for psychological resilience, and they rotate back to Earth after months. Mars settlers are there for years or permanently. How do you maintain purpose and motivation over that time frame? Science provides some answer. You're discovering new things, answering fundamental questions. But science involves a lot of tedious data collection and analysis. Excitement comes in bursts separated by long periods of routine work. Some people find purpose in the community, building something larger than themselves, contributing to humanity's future. But that requires a particular mindset, almost a philosophical or spiritual foundation. Not everyone has it or maintains it under stress. Hobbies and personal projects become crucial. Maybe you're learning a language, writing, creating art, studying something unrelated to your mission tasks. These provide mental stimulation and variety. But again, resources are limited. You can't bring a pottery wheel and kiln. You can't bring musical instruments that require maintenance or create excessive noise in confined spaces. Your hobbies must be compatible with the constraints of Mars life.